Aviation maintenance happens in two radically different settings, out on the line or inside at the base. Out on the active ramp, line maintenance leaves you completely exposed. You are working around the clock against rain, extreme temperatures, and the constant dynamic hazards of heavy airport traffic. Base maintenance moves you indoors into massive hangars. You have shelter from the weather, but the hangar brings its own hazards. You are dealing with the intense echoing of continuous noise, toxic fumes from heavy overhaul activities, and the physical strain of navigating giant scaffolding to reach aircraft components. Both of these environments actively fight against your physical capabilities. When your surroundings are unsuitable or severely uncomfortable, your cognitive focus drops, directly increasing the risk of catastrophic maintenance errors. The hangar is an acoustic trap. Continuous, loud environmental noise actively interferes with verbal communication and easily masks critical audible safety warnings from your colleagues. The human ear has a hard biological limit. If you are exposed to peak noise levels over 115 decibels without ear protection, even for a very short duration, the resulting hearing damage is permanent. Then there are the invisible hazards, the harsh chemical fumes from lubricants, paints, and hydraulic fluids. Breathing these in triggers a deeply ingrained psychological response to escape the irritating smell, creating what we call the urgency trap. When an engineer is trapped in a toxic-smelling area, their instinct is to get out quickly. Instead of stopping to get a breathing apparatus or setting up proper ventilation, they will actively rush through a safety-critical job and cut corners to escape the physical discomfort. Proper lighting is a strict biological requirement for aviation safety. To resolve fine technical details and detect subtle color variations in wiring or fluids, your retina's cone cells require strong, direct light. Natural daylight is highly directional. The aircraft's structure creates deep shadows that conceal critical defects. To fix this, we use artificial task lighting. But poorly positioned lamps create a new hazard, intense glare reflecting off the polished fuselage. Whether you are squinting into an unlit access panel or working under blinding, dazzling reflections, your eyes rapidly fatigue. Operating under either extreme drastically increases the chance that you will miss a critical structural flaw. History shows exactly how physical environments cause accidents. Look at the Northwest Airlines Boeing 747 incident in Tokyo in 1994. An inspector was tasked with checking an engine pylon. The physical location of the scaffolding forced him into a highly uncomfortable position, requiring a 30-degree lean just to see the underside of the wing. The underside of the pylon was supposed to be illuminated by portable fluorescent floor lights, but having been used in the paint shop, they were covered in old paint residue, rendering them almost useless. Faced with a dark workspace and an awkward physical position, the inspector had to hold on to the aircraft structure with one hand to keep his balance while aiming a flashlight with the other. This severely hampered his inspection, and he missed a critical defect on the fuse pin retainers. 4 years earlier, the British Airways BAC 111 accident showed how poor lighting interacts with human positioning. A newly replaced windscreen blew out mid-flight because 84 of the 90 securing bolts used during maintenance were smaller than the specified diameter. The shift maintenance manager had retrieved those parts during the night shift from an unmanned stores area where the ambient illumination was exceptionally poor. To access the drawers on the parts carousel, the manager interposed his body directly between the only light source and the hardware, effectively blocking out what little light remained. Operating in these heavy shadows and failing to wear his spectacles, he skipped reading drawer labels. Instead, he attempted to identify the replacement bolts by visually comparing them to the old ones in the dark, cementing a fatal error. This graph shows the relationship between climate, temperature, and human performance. Following an inverted U-curve, our physical and cognitive abilities peak strictly within a comfortable, warm, and dry baseline state. If you shift into hot and humid conditions, the body works overtime to cool itself through excessive sweating. Losing up to 12 grams of vital salt daily, this rapid physical fatigue triggers a dangerous drop in cognitive concentration. Move to the extreme cold, and the physical effect is equally severe. Freezing conditions numb the extremities, completely destroying the manual dexterity and tactile sensitivity required to work on delicate aircraft components. When subjected to extreme temperatures, your body hijacks your energy just to survive the environment. It leaves you with insufficient mental bandwidth to execute complex maintenance safely. Beyond temperature and light, the very ground you stand on affects your performance. Working at extreme heights on mobile access platforms like scissor lifts naturally introduces sway and instability. When applying force to a component causes the entire platform to move, a significant portion of your brain's attention is hijacked. Maintaining your physical balance leaves far less mental focus for the maintenance task itself. There is also severe, localized physical stress. The continuous use of heavy pneumatic tools, like rivet guns and heavy drills, transmits high-frequency vibrations directly into the arms. Chronic exposure to these heavy percussive tools damages local blood vessels and nerves. This leads to an irreversible medical condition known as vibratory-induced white finger syndrome, or VWF. VWF is a career-ending hazard. It permanently destroys the tactile sensitivity and grip strength that a technician absolutely relies on to safety wire components, torque bolts, and ensure overall airworthiness. All of these environmental stressors converge when you enter the most extreme maintenance setting, confined spaces. Technicians frequently have to navigate highly restricted areas, like crawling through small access holes to inspect the interior of a wing fuel tank. These spaces are not designed for continuous human occupancy. They severely restrict your physical movement, limit the use of your tools, and can trigger deep psychological stressors like claustrophobia, all of which rapidly degrade your efficiency. This diagram illustrates the mechanics of the working environment. It functions as a system of interlocking gears, where physical constraints, social dynamics, and individual stressors all move together to dictate a technician's performance. Because these factors have a profound impact on human capability, European aviation regulations draw a hard line. EASA Part 145 mandates that organizations must ensure the physical working environment is appropriate for the task. The conditions must never be allowed to impair a technician's effectiveness, because guaranteeing their focus is how we guarantee the flying public's safety.